So really the core here is 1 to 4, that's what I'd really like you to understand. Okay, so we're going to start off with a brief introduction to what dynamic programming is, what it means, and then I'm going to talk about, we're going to step through some different approaches. We're going to step through, first of all, policy evaluation. This is the problem of how to understand, how to get the value function for any given policy. So you have a way to behave in some markup decision process, and we want to know how good is that way of behaving, how much reward will the system get by following some given behavior. And then we move on to control methods, so section 3 and 4 of control methods. These are methods for trying to understand not just how much reward will the agent get for some given policy, but what's the maximum amount of reward the agent can get. And the basic idea is in section 3 we'll build on the policy evaluation methods from the previous section. So we'll actually look at, these are based on the two different Bellman equations for expectation and optimality that we saw last time. And then we'll move on to some extensions and theory time allowed. Okay, so let's start with the introduction. So what is dynamic programming? It's a slightly strange name. It sort of it invokes all these different ideas to different people. So I think it's worth just dwelling on what is meant by these two words in dynamic programming, just so we understand, well, why is it even called this? So by dynamic, what's meant is that there's a sequential component to the problem. But we're not just talking about some static problem, but the problem itself has dynamics to it. So theoretically, you might imagine there's some robot moving through some system, and that system has some dynamics to it. Maybe you've got a fish trying to go through some water, and there's some more dynamics to the water and the way it moves. And by programming, we don't mean writing a piece of code, we mean the mathematical meaning of programming here, which is optimizing a program, where a program essentially means a policy, a way to behave. And this is the same sense of programming that's used in like linear programming, quadratic programming, non-convex programming, which you might come across in sort of convex and non-convex programming, which you might come across in some of your other machine learning classes. And it basically just means a method for solving complex programs. That's what programming means, for solving complex problems. And dynamic programming is essentially an approach to sort of look at some difficult problem and say, hey, we can take this difficult problem and make it easier by divide and conquer, by basically dividing it up into subproblems, solving each of those subproblems, putting the pieces back together and solving the overall problem. That's the core idea of dynamic programming, is divide and conquer. So how does that work in practice? What do we really need in order for dynamic programming to work? So it's a very, very general solution method, and we're not going to talk about in its full generality. We're going to talk about how to apply this approach specifically to solving reinforcement learning problems. But in general, it's worth understanding, well, when can you apply dynamic programming? And we basically just need two properties to exist for the problem we're trying to solve. One of which is called optimal substructure. What does that mean? That basically means that something called the Principle of Optimality applies, which basically means that the optimal solution can be broken up into pieces, each of which is sort of an optimal solution to its own subproblem. So that's the principle of optimality. You can start with some big problem, like getting from A to B, and you can say, okay, well, in order to get from here to the top of this staircase, I first of all need to get halfway up the staircase, and then I need to get from halfway to the top of the staircase. Now I've got two much easier problems. If I can solve those two problems, I can put the pieces together and solve the overall problem. So that's optimal substructure. And the second requirement is that some of those subproblems overlap. So that basically means that the subproblems recur many times. In other words, that by breaking it down into subproblems, I actually gain something because these subproblems will be reused more than one time. So if I figured out how to climb up the second part of the stairs, and now I need to climb up those stairs from all the different ways I might reach that middle point. Maybe there's a gust of wind, I get blown over to there, and now it's still useful to know how to get up the stairs from wherever I end up. Okay. And the idea is that if you have overlapping subproblems, then we can sort of solve these subproblems, cache the solutions to those subproblems, store them somewhere, and then reuse them whenever we need to. So what does that mean in our MDPs? Well, MDPs actually satisfy both of these properties. So it's the Bellman equation itself, the Bellman equation that we looked at last time, that actually gives this recursive decomposition. So what we'll see later is that the Bellman equation itself satisfies this principle of optimality and can be broken. The Bellman equation is the way we break things up into pieces. We break it up into the reward you get for one step and then the value of everything you do after that. So that's the way we're going to break things up into the first step. We want to behave optimally for one step and then behave optimally after that step. And the value function is the thing that stores and reuses solutions. So the value function is our cache. The value function is the thing that says, well, I've worked out how to get from one state to the end of the problem. So now can I reuse that piece of my solution to help me work out the value of other states? Okay, so we'll have more details later on, so hopefully this will become apparent as we go. But this is like a very general, top-down sort of Hawkeye view. Okay, so what we're going to do, how are we going to use dynamic programming? Well, we're going to try and do planning. So what's planning again? So I mentioned this in the first lecture, but planning is basically the problem where you're given the structure of the problem. You're told the dynamics of the problem. You're told the MDP. You're told the reward function. You're told the transition model, the MDP. And now we want to find the optimal way to behave in that known problem. So that's what we're going to do. We're going to do planning. And there's two planning problems. We can do this for prediction. So basically, prediction means that you're given as input the MDP. So you're told the state space S, the action space A, you're told the transition matrix P, the reward function R, and the discount factor. And you're given some policy for prediction. Like you might be told, I'm going to follow some particular behavior. I'm going to follow a random walk up to the top of this route. How long is it going to take me to get to the top? Or I might be given a Markov reward process rather than MDP. Remember, this is just the thing where the action space has been factored out. So you can flatten an MDP into one of these. So if you're given a Markov reward process, you can just say how much reward am I going to get in that process. And the output is a value function. So how much reward does the system expect to get from any state just following this policy that's been given, or following the Markov reward process until the end? How much reward is it going to get? How good is it to be in any state? So that's what planning means, to find this thing, this value function. So that's the prediction part. Then we're going to look at control. We're going to use dynamic programming for both of these things, for prediction and for control. What does control mean? Well, control means we're given the input, given the MDP, the state space, the action space, and the dynamics, and the reward. And now we're going to output the optimal value function, not just the value function for any given policy. Now the policy is not an input. We need to work this thing out. So we're going to sort of search over this, that we need to find the maximum reward we can get over all different strategies we could choose. So we're going to output two things now, which is this optimal value function and a corresponding optimal policy. And remember, there's just one unique optimal value function, and if we find that determinant, that gives us straight away an optimal policy. Okay, so that's the goal. And we've come up with a couple of methods for solving these things. We'll see a few ways to do this as we progress. Okay. So dynamic programming at a very high level scale is used to solve many problems, and planning in MDPs is just one of them. Some examples which you might come across might be scheduling algorithms, string algorithms like sequence alignment. These are very popular now with genetics. Graph algorithms like shortest path algorithms and so forth. Graphical models. You may have come across something called the Viterbi algorithm. Well, actually, that's another instance of dynamic programming. Bioinformatics, we get things like lattice models. Dynamic programming is very, very widespread, and all of these things satisfy these sort of this divide and conquer principle where there's some optimal substructure, so there's some subproblems that can be reused and applied elsewhere. Okay, so now we're going to start with the prediction problem. So the problem which we're going for now is we're given this policy pi, and we want to work out what's the value function corresponding to this policy in our MDP. Okay, and the way we're going to do it is we're going to take our Bellman equation from last lecture, the Bellman expectation equation, and we're going to turn that into an iterative procedure. So to solve the Bellman equation, we're just going to iterate on this thing. And so we're going to start off with some arbitrary value function, v1. And what we're going to do is we're basically going to pass that through the Bellman equation to give us a new value function, v2. We're going to pass that through the Bellman equation again, give us a new value function, v3, and so forth. And what we're going to see is that this process actually is going to converge onto the true value function. Actually, I'm going to defer the theory to the end of the lecture. And the idea is we're going to use something called synchronous backups. This is a way of turning our Bellman equations into updates. So backup just means an update. So each iteration of this algorithm, what we're going to do is for every single state in our state space, we're going to update the value function at this state S for the new iteration from where we ended up. So we're going to look at some successor state, S prime. So you're in some state S and you want to know, well, how good is this state? And what we're going to do is we're going to look at the successor state, S prime. And we're going to use the value function we had for S prime to give us a new value for S. So synchronous backups means that we do this for all states in our state space sort of simultaneously at once in each iteration. And we'll talk later about asynchronous backups and what advantage they may give. And we'll come back to the theory. Okay, so here's our Bellman equation again. So the way we can think of this Bellman equation is, again, I put up these diagrams, flashed them up briefly last week. But essentially what these diagrams mean is they're sort of like, they're look-ahead trees. So if we imagine that we're considering one state S at the top of the tree, at the root of the tree there, and we want to know, well, what's the value, b pi, of this state at the root of the tree? Well, we can figure out that value by doing a look-ahead, a two-step look-ahead, where we can imagine for all the actions we might take, that's looking ahead to these two black dots. And from there, for all the successor states the environment might push us into, what's the value going to be? And that gives us this Bellman equation here. So now we're not going to do this as a Bellman equation, we're going to do it as a backup. We're basically going to say, we're going to set the value at the next iteration of this state here to be equal to this look ahead, where we're evaluating the leaves now of this thing are going to be evaluated, so the value of the leaves is going to be given by our previous iteration. So we're going to start off with some value function, vk, and we want to work out vk plus 1 for this state at the root. And we assume that we've given vk of s prime the value of each of these leaf nodes here. So how do we do that? We just apply our Bellman equation. We do a look ahead. We say we're going to look at one step. We're going to sum over all the things that we can do times the probability of taking that action. This is our policy. And then we're going to add up the reward that we would get taking that action from the root, plus the discounted next state that the environment might take us to. So this is just an expectation over the next state. So this is summing over these final transitions there of the leaf values. So we start with some value of the leaves given by a previous iteration. We propagate that information up, and we get a new value of the root. And what we're going to do is we're going to apply this for all roots, for all states S. So each state gets to be a turn, take a turn to be the root of this diagram. And this is all done in parallel for one iteration. So that's that's how we turn a Bellman equation into a backup, into an update. Okay, so let's make that a bit more concrete by taking an example. So we're going to start off with, we can have some sort of grid world examples. Grid worlds are, although they're not very representative of the real world, they're very easy to understand what's going on, and you get quite a good flavour of what's happening. So this grid world here basically has these 14 different states in white, and then 2 terminal states in grey there. So if the agent gets to those terminal states, it's done. And what's going to happen is it gets -1 reward for every step that it takes. So it's basically just trying to get to those grey states as quickly as possible. There's no discount factor, so in other words, gamma is set to 1. We can do that because all the episodes terminate, so there isn't this problem with infinite rewards. And we're going to consider and if it tries to take an action that would take it off the grid, it just stays where it is. So it still gets a reward of -1, but it stays where it is. And we're going to consider a uniform random policy that with probability 0.25 goes north, east, south, or west. Okay, so how can we evaluate this by our iterative policy evaluation algorithm? Well, this is kind of what it looks like. We're going to start off, we can start off with anything as our first policy. So we're going to start off with 0 everywhere, for iteration k equals 0. And just for a second, ignore this column here. I'd really like to focus first on this column here, just to understand what's going on. So k equals 0, we start off with initializing the value function to be 0 for all states. And now we're going to apply a Bellman equation to all of those states in iterations to update the value function sort of everywhere at each iteration. So at the second step, what's happening? Well, if we start in any one of these states in the middle, and we look in each direction, we can look ahead and we can say, okay, well, if we go north, east, south, or west, we'll get -1 reward for taking that step. So it costs us -1 to take that step. And then we'll end up in a state where we predict that we'll get 0 reward. So if we add those together, we basically end up predicting -1 for all of those. And the only ones where we get something different are these corner states here. Or in the corner states, if we look ahead now, we can look ahead one step and we can see basically, well, I guess we've already terminated there, so it's just 0 there. Okay, so now if we go to the second step here, Again, we can sort of look ahead, and again, if we start from one of these middle states here, we can look ahead one step and say, okay, well, if I go north, east, south, or west, I'm going to end up, it's going to cost me -1 to get there, and I'll end up in somewhere that we think, from our previous situation, had a value of -1, and so our total value will be -2 from each of these 4 states here. If we take one of these states here, I think this should be -1.75, there just wasn't spaces for that to print properly. There's basically 3 different actions we could take. If we go north, west, or south, we'll end up back where we are. In each of those cases, there'll be a cost of -1, and we'll end up somewhere, we predicted -1, but there's also a 0.25 chance of going east, in which case it will still cost us -1, but we'll end up somewhere we predicted had a value of 0. So now we get -1 3/4 for that one. And we keep applying this procedure. So this is after 3 steps. This is after 10 steps. This should say infinity. This is what the whole thing converges to. And it turns out that this whole thing converges to the actual true values. So it's actually quite bad to start in the middle somewhere like this. Actually, it's about -20. It takes about 20 steps following a uniform random policy on average before you terminate in one of these corner states. And so just by this very simple procedure, iterative application of the Bellman equation, we're able to solve this straightforward problem. Okay, now let's look at the second column. So what's interesting about the second column is now we're going to use this to generate a policy. So this second column basically says, if we were to use our value function there to generate a policy, what's the natural thing to do? Well, the natural thing to do is just to pick the actions greedily with respect to our values. So that basically means that if the agent's here, and it's going to act greedily, it's going to look around it and say, okay, I could go there, that would get me -2, could go there, that would get me -2, there -1.7, there -1.7. So now it says, okay, well these 2 actions are equally good, so any policy that takes one of those will be optimal. And so that's what's indicated by these arrows here. And so these sorts of arrows indicate the the greedy policy with respect to our current value function. So these values are not yet accurate, but we can still use them to generate a policy. And what we see is we start off with completely uniform behavior where we have this uninformed policy to begin with, we don't know what to do, so we start off randomly. But we start to get better and better and better, and actually it only takes us 3 iterations of this algorithm before the greedy policy is already optimal. So that's actually the optimal policy, and it's a very small grid world. But the point is, even though the values are still way off optimal, we already got to greedy very quickly, and we'll use that idea later on. Okay, so what we've been leading into now, so we started off with an algorithm that was just for evaluation, but what you can see we're leading into is an idea for control. That we can already use this very simple idea for evaluation to help us do control. And you've probably already got the idea of sort of how it's going to work, but let's make that explicit now by talking about an algorithm called policy iteration. So this is our first approach to solving an MDP and actually doing the whole control thing and finding the optimal policy. Okay. And what we need is an idea called policy improvement. So policy improvement basically means that you start with a policy and you somehow make that policy better in all states. So we're going to start off imagining that we've got a deterministic policy where just for each action A we take a policy and it takes us from state S to some, we'll always pick that action A. Okay, so the idea is that we can improve that policy by acting greedily. So that simple greedy idea I just showed you in that illustration is actually guaranteed to improve the policy. So in other words, this pi prime from S, if we just maximize, so if we know the action value function, so Q, remember, is the value function which tells us if we were to start in state S and then take action A, how good would it be, how much reward would we get? So to improve the policy basically means maximizing over these Qs. We pick the action that's going to give us the most reward from state S under policy pi, under our old policy pi. And now we're going to use that to generate a new policy, pi prime. That's the idea. We'll do a step of policy improvement. Okay. Now just a little bit of theory, so bear with me for a second. What we really need to show is just one key fact, which is that this is guaranteed to improve the policy everywhere. In other words, what we want to show is that this, the value of pi prime is at least as good, greater than or equal to, the value function that we started with in pi. And so the way we're going to show that is just by looking at the action value function. In other words, this is our sort of greedified policy, the thing where we're going to pick actions for one step using our new thing pi prime, and then we're going to carry on using our normal policy pi. That's what it means to be greedy. It's like for one step, we're going to act according to the best thing there. Okay, so maybe I'll just give some sort of outline this theory, and you can look at it more in detail afterwards. But the rough outline is to say, okay, if we were to follow this new policy pi prime, well, what is that new policy? It's basically, our new policy was to maximize with respect to our old policy. That's what it meant to be greedy. So that's this max here. This is just defining the greedy policy. It's the thing which picks action so as to maximize the value under our old policy pi. And now if we're maximizing over A, well, we know that that has to be at least as good as, so we're maximizing over A, so that must be at least as good as an arbitrary A. And so the arbitrary A we're going to plug in is the A that was chosen by our old policy, pi of S. But if we look at this thing, this is now the thing which says Q pi basically means what happens if you follow this action for one step and then behave according to that policy afterwards. But we're using the same policy to pick the first action as we are to continue. In other words, this is the value of just following policy pi all the way through, which we call V pi. So we've sort of showed that, that by using pi prime, by acting greedily for one step, that we've improved the value from that one state, over just one step. And now all we need to do to sort of show that policy improvement works is we need to unroll this over many steps. So this shows the fact for one step, this shows that by acting greedily you get at least as much reward for one step, and then you sort of unroll this over many steps. So this is just the unrolling. So basically just apply this same inequality that we've got here, this Q pi greater than or equal to V pi, but we unroll it, and we apply it to every step through time. And that unrolling basically shows us that the value function is theorem proof, the value function itself, the whole value function looking all the way ahead must be at least as good. So what's the point of this? The point is really to show one sort of major fact, which is this simple idea of acting greedily with respect to our current value function is enough to guarantee that we're making progress. So do we know that we're making progress to something unique? Well, one thing we can say is that if improvements stop, in other words, if we get to a situation, if improvements stop, well, what does that mean? It means that we've actually got an equality instead of an inequality. Otherwise, we'd still have something we could keep doing. We'd still be making progress. And if we stop, then this thing is equal by definition. So this is just that same thing we had before, but with the inequality there replaced by inequality. So if improvements stop, that basically tells us what? Well, it tells us that we've satisfied the Bellman equation. We've satisfied the Bellman Optimality Equation. Because basically, V pi is equal to this max Q pi. So just the second and last terms we've pulled out of this equality. And that is one of the versions of the Bellman Optimality Equation that we had in the last. So this is actually the definition of optimality for V pi. So really what I want you to have a sense of, if we just sort of step back from the math, what's it really showing? It's showing that there's always progress that can be made until you reach equality on this thing, at which point the Bellman Optimality Equation is satisfied, and we can therefore show that we've actually reached something that's really optimal. Okay, so policy improvement, we're going to keep improving the policy, it's going to be making progress, and eventually we're going to get to something which is absolutely guaranteed to be the optimal policy. So it's sort of an amazing result that just by the simple idea you always make progress. Any questions on that part? Is that clear to people? Okay. Is that a question? Okay. So what we're going to do, so that's the theory, how do we turn this into an algorithm? So really what we're going to do is exactly what we saw here, where we're going to sort of run our iterative policy evaluation algorithm, and then at a certain point we're going to basically say, okay, we've reached some policy, we've reached, now we're going to basically move over to this right-hand thing, we're going to say, okay, that's going to generate us a new policy, and now we're going to evaluate that policy. And we're going to run that evaluation for a while, we're going to generate a new policy and so forth. So let's see how that works. So that gives us something called policy iteration. Policy iteration is basically a very straightforward idea of interleaving two separate algorithms. The first one is the iterative policy evaluation algorithm that we just were looking at in the first section. In other words, how to evaluate our current policy. So we start with some policy, but we want to evaluate that policy. And then we can improve that policy. So basically, we're going to, given our value, we can now generate a new policy by greedy policy improvement. So we act greedily with respect to that thing. So we're sort of interleaving, we're going round and round this loop where we start off with a value function and a policy. So that's the starting point here. We start off with some value function and some policy. We evaluate that policy. That takes us to the top of this diagram. That gives us a new value function. That new value function gives us a new policy by acting greedily with respect to that value function. That policy gives us a new value function by evaluating that new behavior. And that new value function gives us an even better policy. And this process iterates and iterates, and we get closer and closer and closer to the optimal value function and the optimal policy. And this thing really converges on the optimal way to behave for the MTP. We go round and round this loop, evaluating the current policy and then making that policy better iteratively. So that's the sort of key idea. So let's make that a bit more concrete with an example. So this is a problem called Jack's car rental. This is in the Saturn Barto book. So there's basically, in this example, you've sort of got to imagine there's two locations in this sort of car rental company, each of which can have up to 20 cars in each location at a time. That's sort of the capacity of their car park. And what you can do is you can basically move cars between these locations overnight. And you want to move them around between these locations so that you get the maximum sort of income. And you get income of $10 for each car that you rent. But you can only rent a car if there's actually cars in your car park to rent. And the problem is that these cars are returned and requested at different rates from the two different locations. And so basically, they're Poisson, but basically one of them, cars come in at the same rate that they go out, but in the other one, the cars are requested much more often than they're actually returned. So the idea is you need to sort of shift the cars over from the car park at which they come back more frequently to the car park at which they're requested more frequently. And you need to figure out, well, what's the optimal income in this problem? So this is, actually a really good example of how dynamic programming is actually used in practice to solve, interesting sort of, operations research type problems or things like that. And this is applying the policy iteration algorithm to this problem. So what we do is, again, we start off with just an arbitrary value function, which is 0 in this case. And what we're looking at here is 1, 2, 3, so basically 4 iterations of the policy iteration algorithm, and only at the end are we showing the value function after 4 iterations. So you could, in principle, have shown this value function at each step because we're evaluating every single step. But this is basically just showing the policies. And the policies here are, the axes of this diagram are basically showing how many cars there are at the first location on this y-axis, how many cars there are at the second location on the x-axis. So this is the whole state space now. You either have 10 cars at one location and 10 cars at the other location, or some other combination. And now the question is, well, what's the optimal action? How many cars should you move from one to the other if you're in one of these states? And so we start off with no idea. We start off just guessing and saying, well, let's start off with 0, trying not moving anything at all. We evaluate that gives us a value function, and then we improve our policy, and it gives us that first sort of set of contours over there, which tells us our first guess at when we should move 1 car over, 2 cars over. And what happens is that we then evaluate that, we get a new policy, and the contours start to move around until eventually we end up with, as you can see, these things have sort of converged now. We've actually ended up with the optimal policy after just, I think, 3 iterations of the algorithm here. And the value function actually looks like this, so it has quite a smooth kind of characteristic. So this is actually the optimal value now in this problem. This is how much reward you could ever manage to get in this particular problem by moving cars around at just the right rate. So we've solved the MDP, the problem is solved. Okay, is that clear? Yeah.
One question, in that iteration, do you iterate each of the steps to convergence and then do the next one, or just do one of each step as you go around it?
In this example, it was iterated to convergence. So the policy evaluation, the iterative policy evaluation was iterated to convergence, and then we updated the policy. We'll talk about the other idea later, to hold that thought. Okay, get back to this slide. leading right onto this slide. So does the iterative policy evaluation actually need to get all the way to the true value for that policy? Or should we stop a bit earlier? So what's the motivation to this? So you could stop a bit earlier if you wanted to say, okay, well, we don't need to actually spend all this energy getting exactly the value function for that policy to 100 decimal places. Maybe we should stop a little bit earlier, because probably the policy is already going to be fairly good. So maybe you stop when the value function is within epsilon when it's not changing by more than epsilon in any given step. That would be one idea. Or you could just stop after k iterations. You could say, okay, well, I've run my iterative policy evaluation. I've applied my Bellman expectation equation 10 times. Maybe I'm just going to stop after 10 times and then improve the policy. Do another 10 steps of policy evaluation and then improve the policy. So we kind of saw the motivation for that in this small grid world example. We just go back. So if you remember here, it only took us 3 steps of policy evaluation. We only needed to iterate. So we were just using one policy here. This was uniform random. And after 3 steps of applying this algorithm, we already had the optimal policy. So we could have spent all these other steps trying to get better and better, more accurate values, and the value would have changed a lot, but it wouldn't have made any difference to the algorithm, because the policy that we're getting by our greedy policy evaluation would have been the same. So, so that leads us to the idea of modified policy iteration. So a natural question then is, well, what happens if you take this to its extreme? So why not update the policy every iteration? So choose k equal to 1. So we just do the minimum amount of work in updating our value function, and then we improve the policy straight away. And in a sense, this is the natural thing to do. If you've got new information about how good the states are, well, why wait to use that information? Just improve your policy straight away. And so we're going to use that idea sort of more and more throughout the course. But the first example we'll see is value iteration, which is the very next section, which is exactly equivalent to that idea. We'll improve the policy step. Okay. We're also, another idea we're going to use a lot throughout the course is this idea of generalized policy iteration. So what we used so far was we used particular algorithms for policy evaluation and policy improvement. But we can use any algorithms for policy evaluation and any algorithms for policy improvement, and the same idea will still apply. So we can evaluate our policy any way we want, and that will take us, from some initial starting value of policy, we'll get from that policy to some value function. And now we can improve that policy in any way we want. As long as we know we're making progress, we're happy. Greedy policy improvement is not the only way. And now we can iterate these two ideas and go round and round and round, and we'll still converge on the optimal value function, the optimal policy, as long as we're actually really evaluating the policy and really improving our policy. So that's the idea of generalized policy iteration. Okay. So value iteration. So I'm going to go back to the sort of principles of dynamic programming for a minute, just to introduce the idea of value iteration. So let's consider a very, very sort of common, well-known problem, which is what's called the deterministic shortest path problem. And this basically means you've just got, say, some maze, and you want to know how to get to the goal state from the start state with the minimum cost. And there can be, it's basically you've got some graph, and you're trying to navigate through that graph and minimize the total cost of the edges to get from the start to the goal. And so we can think of this as a kind of an MDP, but it just happens to have deterministic transitions. And it's got some negative, so it's got some rewards, which are the same as negative costs. And we're going to assume for now it's undiscounted, just to keep it simple. Okay. Then there's this theorem, which is the principle of optimality. The theorem's more general, but we'll see that later. And the basic idea is that if you have some path, so it's a very sort of intuitive idea, which basically says, so basically we've got some start and some goal state here, and we're considering some sequence of actions here, which takes us through all these states and actions. So this would be S1, A1 takes us to there, S2, A2, all the way through here. And the basic idea of the principle of optimality is that this path is only optimal if for any state ST that we pick along here, it's only optimal if this subpath here is also optimal. Because if this wasn't optimal, then that suggests that that must mean that there's some other path which is optimal. And so this whole path can't be optimal because there'd be a better path to take. Okay? Fairly natural idea. That's the principle of optimality. And so all we're going to do is we're going to apply the principle of optimality, but just instead of breaking up at an arbitrary point, we're going to break up after exactly one step. So we're going to break here, and we're basically going to apply the same principle, that this whole path can only be optimal if this path is optimal. There's another way of saying that, is that an optimal path from here consists of two things. An optimal first action, followed by the optimal thing to do from there onwards. And so that means that we kind of have this is like a simplification of the Bellman equation, just for the deterministic case. It basically tells us that the optimal value function, that's basically the cost all the way along the path. So if we're starting in S1, the value function from here, or the value function from any state, must be equal to the maximum. This is the optimal first step, this maximum over the reward function, plus the optimal way to behave from there onwards. Again, the idea is very simple, that if there was some other better way to behave, then the overall optimal thing would have to follow that one instead. So this is sort of an intuition to why the Bellman optimality equation must be true. The principle of optimality applied to one step. You have to take the best thing for one step and the best thing from there onwards. Okay. So another way to say that is that if we know the solution to these subproblems, if we already know the optimal value function to here, then it's straightforward to figure out the best next action to take. Because we can just consider all these other actions we might take that could take us to here and here, and we just look for the one that's going to give us the best overall result. And because we've already solved for this subproblem, we know we've solved for this subproblem here, we've solved for this subproblem here, we know that we can just pick the one that gives us the best, that we've already got these V star of S prime, these successors. All we need to do is consider over one step which of these is going to take us to the best successor state, plus the reward along the way. So that's the principle of value iteration in this deterministic case. We can just construct the solution by maximizing over this one-step reward plus the optimal value function from there onwards. And so intuitively we can do this by applying this same update backwards from the end of the problem and sweeping backwards until we so you start at the goal or the horizon, you sort of walk backwards through the whole problem. So you can imagine sort of dividing this up into stages, and you first of all figure out the optimal value for this stage, and then you use your optimal value for that to solve for this, the value function here, you use your optimal values there to solve for your optimal value here, and so forth. We're sort of working backwards. So here's a little example to make that bit clearer. Again, very simple grid world. Now there's just one goal state, this grey state here, and similar idea to before, -1 for each action. And we're going to start off with, again, a zero value function everywhere. And now all we're going to do is we're going to sweep backwards from that goal state and update our value function. So all we need to do is to say, okay, in this V2, we're going to look one step ahead and say, okay, if we were to look one step ahead, what's the best we could do? Well, we're looking one step ahead from, say, one of those middle states. The best you can do is you have to take a -1 transition somewhere. So we end up with this -1 everywhere except at the goal state. But if we were to look now in V3, we could look one step ahead. We could say if you were to start in the middle state, one of the middle states, well, you take one step anywhere, and then we believe we've got the optimal value function from there already. So we're sort of sweeping out from the top left towards the bottom right, if you see what I mean. So we're basically filling in values, starting at the top left, sweeping through to the bottom right, working backwards from the goal. Now, we want to apply this to MVPs, and MVPs don't usually have a finite horizon. There's no particular, there's not necessarily one goal state. There could just be a general reward function everywhere. We want to keep going and get as much reward as possible. And also, they can be loopy, so you can go round and round to the same state again, or find your way just looping around. We want to allow for all these cases. And so we can't use this idea of just working backwards, but from the end towards the beginning, but we can still apply the same idea. And the same idea still applies, that we sort of take what we had, propagate information backwards, and we use the Bellman Optimality Equation now to back up the value function from the successor value function. And so if we think about how dynamic programming is working, we're still using like a divide and conquer principle, where the subproblem is now, the subproblem is solving the value function from the successor state. And there's a sense in which that's an easier problem just because of the discount factor. That's what comes up in the theory. And then we just iterate this idea until convergence. Okay, so basically what we need is an extension to the principle of optimality that isn't just for this deterministic case, that allows for stochastic transitions and allows for looping and so forth. And that's this principle of optimality here. So this is a much more sort of general version of it. And now we're talking about policies rather than paths. We can't talk about paths because we don't know what the environment's going to do to us. It's stochastic. So we don't know if we try to take some action, we might actually get pushed off over here somewhere, and now we need to find a way to get back to the goal again. So we need to consider policies that, well, this is sort of what we call closed loop rather than open loop. That we need a policy is something that can respond to any situation it might end up in any state, and tells us what actions to take. And the policy is optimal if and only if, for any state that you can reach from S, that policy, so we can still use the same idea, and basically say if we get pushed off into some state over here that's reachable from the start, then basically we can say that the policy that we have, the policy is optimal if and only if the policy from here is also optimal. In other words, this is reachable, and the value function of this, how we get back to here, is itself optimal. So it has to be the case that for anywhere we can get pushed to, the value function from that point to the goal is itself optimal, or just the value function. There's not even necessarily a goal here. So the value function of where we get pushed to has to itself be optimal. And if that isn't true, it can't be an optimal policy, because there'd be something better to do from that state that you could get pushed to, and therefore your overall policy wouldn't be optimal. Okay. And so again, that tells us that if we just break this up after one action, that again tells us that an optimal policy must consist of an optimal first action followed by an optimal policy from the successor state. So this is now the full version, the stochastic version of the Bellman Optimality Equation. So this is kind of, we saw this last lecture, but this is sort of deriving the same thing from this principle of optimality. That now we're saying that if we maximize over one step of reward plus the expected value, this is all the transitions that we can be taken to, all the probabilities of going from S to S prime when we take action A. These are all the optimal values of where we end up. And by the principle of optimality, this has to be true. It has to be true that if you take an action wherever you get pushed to, it has to be equal to this optimal value from there onwards. We're breaking up the path into one step and then the rest of it. Okay. So, how do we turn this into an algorithm? So this lecture is supposed to be about algorithms. So we want to now solve this control problem. So we want to find the optimal policy. And the solution we're going to use now is, unlike the previous two sections where we iteratively applied the Bellman expectation equation, now we can take the Bellman optimality equation and we're going to turn that into an iterative backup. So we start off with some value function b, b1. We're going to iterate our Bellman optimality equation to give us a new value function b2. We're going to iterate with our Bellman optimality equation again, give us b3, and so on. And what we're going to see is that actually gives us the optimal value function b star. So we just keep applying our Bellman optimality equation, make this thing better and better, and we'll get b star. And we use synchronous backups again. In other words, we just do this over the entire state space at once. So the algorithm looks a bit like this. So each iteration, we're going to apply this idea to every single state in the state space. So we're basically going to update the value of the current state from our estimated value at the next state. And we're going to use the Bellman equation to do that, the Bellman optimality equation. So what's interesting here is, unlike policy iteration, this whole algorithm works without ever explicitly saying what the policy is. We're not even writing down the policy, we're not storing this thing in memory, we're not talking about policies here. This is all done just in value function space. We're just moving through value functions until we end up with the optimal value. And if we ever want the policy, we can get that out from the value function. But the whole algorithm works in value function space. And what's interesting is that actually some of the steps along the way might not actually correspond to any policy. But what we get out at the end is guaranteed to correspond to an optimal policy. So let's go back to our backup diagrams. So we've got this diagram here, then we're doing some look ahead. This arc at the top now means like a maximization, and that's what this arc means in these diagrams. So we're doing a look ahead from state S at the top there, doing a look ahead using these equations here. We're basically doing a look ahead to say, we're now doing this iterative backup where we're going to use, at the leaves here, we're now going to use our best estimate of the optimal value at the leaves. So that's our previous iteration k, and we're going to estimate the value under our previous iteration of s prime. Now we can do this look ahead and say if we were to look ahead one step of actions and one step of successor states and use our previous estimate of the value of the leaves, what would that look ahead estimate for the value of the state? And so that's basically what this is saying. Maximize over all the actions we could take. That's this sort of first arc here. And now take an expectation over all the things the environment could do to us. So this is probability of transitioning from S to S prime under that action A. So we're going to just apply this Bellman Optimality Equation. And again, every single state in the state space gets a turn to be the guy at the top. And we do this all simultaneously because we're doing synchronous value iteration. So they all get a turn, they all get the chance to be the guy at the top in each iteration. Okay.
So how is it really different from policy iteration with one step update? So in practice it says the same thing.
Okay, policy iteration didn't have the max. So do you mean iterative policy evaluation? So this algorithm where we were doing the same thing but with the Bellman expectation equation?
Yeah.
Okay, so that was just evaluating how good a given policy is. And so what we had, instead of this max, we had the Bellman expectation equation, which was an expectation over what would happen under the actions that we take under that policy.
But after that, when you update the policy, then you take the max.
So when we did the policy improvement, you mean?
Improvement, yeah.
Yeah, okay, so what's the difference between value iteration and policy iteration? That's the question. That's a good question.
Yeah.
So value iteration turns out to be equivalent to this idea. We had this idea that you don't need to go all the way to the end of evaluating something. So value iteration is the same as policy iteration, where you only take one step. Where you only do one step, you sort of immediately update your policy after just one step of evaluation. And then the two algorithms become the same. Okay, so it's another way to think about the same idea, really. And I think there's something very useful about understanding that you can either think of the Bellman optimality equation or Bellman expectation equation as two ways to do control. So there's these sort of two paths sort of go all the way through reinforcement learning. So we'll take both paths several steps in later lectures as well. Does that help a little bit? Okay. So it's like modified policy iteration with where k is 1. Basically is effectively the same. Just checking. Okay. Okay, so here's a demo that I borrowed from someone else's website, which is always handy. Okay. So, I'll just see if I think we can just about see. Okay. So what's going on here? We've got another grid world, and basically what we're going to do is apply value iteration to this grid world problem. And it turns out that this grid world, you get, again, -1 per step. Most of the time, when you take an action north, east, south, or west, it does what you want, but there's some stochasticity in the environment. So with probability 0.7, you go the direction you want, and with probability 0.1, you go in each of the 3 directions that you didn't want. And there are 4 sort of so you get -1 per step, but there's also 4 kind of rewards hidden around this grid. I think 2 of which are very good and 2 of which are bad. And what we see is that as we step through, this is now iterations, complete iterations of value iteration. So it starts off with the value function of 0. That's these sort of, the numbers here are 0, and these sort of star shapes of the policy indicating the different directions of which ways you can go here. And what we see is after 1 step, you can see immediately these sorts of goal rewards appear. So you get +10 if you from this goal reward if you happen to start there, -10 from this one, -5 for that one, 3 for this one. But as we iterate forwards, we'll see that information propagating backwards through this system. So as the algorithm progresses, we get sort of sweeping out. It shows up much better on my laptop, unfortunately, on this screen. Okay, at least you can see the green sweeping out from here. I can see the other sweeping out too, but okay. So as the algorithm progresses, you get this sort of sweeping over the propagation of information, and it gets closer and closer. And it's starting to really figure out, these arrows now are really pointing in the optimal directions if you look. And it's getting more and more idea of the value of the states and which way it should go. So every step we're basically just applying that same idea of applying the Bellman Optimality Equation, updating every state one step and improving our estimates of both the value function and implicitly the policy. Okay. So any questions? Okay. So this is a summary of what we've looked at so far before we move on. And this table sort of summarizes first of all, the problems that we're trying to solve. Well, first of all, we tried to solve a prediction problem where we had this idea of applying the Bellman expectation equation, the Bellman equation we used, and the algorithm that led to, when we turned the Bellman equation into a backup, the algorithm that led to was iterative policy evaluation. That was given a policy, you iterate that Bellman equation, and you get iterative policy evaluation as the algorithm. Then we looked at two different approaches to the control problem, how to find the optimal policy. The first one used the same Bellman equation, the Bellman expectation equation, for a given policy, but we combined that by interleaving with greedy policy improvement. This was the sort of the policy iteration idea. So the algorithm's policy iteration, we interleaved, we evaluated by Bellman expectation equation, iterating that thing, and then we improved the policy and iterated through those. And then finally, we also tried to solve the control problem by using the Bellman Optimality Equation and iterating the Bellman Optimality Equation directly, and that led to the value iteration algorithm. So a few comments on these algorithms. So all of these, what we've looked at so far was based on the state value function V. And there's a cost to doing that. What's the computational cost? Well, this just comes from these, if you look at the look ahead, you can see the cost immediately, which is for each state that you start from, there's a cost. You have to consider all actions from that state and all successor states you might get to from there. So from every state, there's a cost of mn, and then for every iteration, there are n states that we're giving a chance to be the root. So the cost is mn squared, the complexity per iteration, for n actions and n states. So, but there's an alternative to this. You don't have to use the value function v. You can also use the action value function q. So if you remember in the first lecture, we had Bellman equations for q as well as for v. The q relates to itself in just the same way that v does. So what happens if you turn q and use the q Bellman equations and turn those into iterative updates? Well, I'm not going to labour the point by stepping through all the same ideas again, but exactly the same algorithms can be applied using q as using v. In practice, that isn't really done in this setting, for the planning setting using dynamic programming. And the reason is the complexity. That sort of intuitively, what we've done is instead of looping over all states in the value function, we now need to loop over all states and all actions, get a chance to be the root. But the cost of each update is still the same. So we've multiplied the cost by m per iteration. And in a sense, we're trying to solve over a larger, we've made the state action space is bigger than the state space. So value iteration works here. So these V's sort of work over a more compact space. They're letting a more compact value function than this one. However, when we move on in the lectures, we'll see very good reasons to use Q rather than V, and that's when we move to the model-free part of the course. Okay, so we're going to move on to some extensions to dynamic programming. So I guess this is a good time to stop. So any questions so far about, that's really, so far that's the core idea, so I really want everyone to understand. So if there's anything that's sort of fuzzy or unclear, it's worth sort of asking and just making sure that we've got those concepts.
So when showing that policy iteration improvement converges, you mean that was before you mentioned the Bellman equation?
Yes.
But would you need that portion that convergence as well?
Section 6, we're going to talk about convergence. So all of these algorithms, it turns out, converge to the, so if we look at this summary table, all of these algorithms converge to the solution to the problem we're trying to solve. I'll outline some theory in just a second. I probably won't go through it all. Okay, so let's do some extensions to dynamic programming. So the first one I really want to just spend a little bit of time on is asynchronous dynamic programming. So far we talked about these synchronous backups, where in each iteration we updated all states in the state space simultaneously. So you can think of this as like a parallel computation, where every state gets a chance to be the root, and it's all done in parallel at each iteration. Whereas in asynchronous dynamic programming, we consider one state at a time, and we can do this in any order. They can be done in parallel, they can be done not in parallel. We can pick to update this state, and then this state, and then this state, and then this state. And for each selected state, we're going to apply the backup corresponding to just that state. And then we're going to use that new value function to update the next state. And it turns out that if you pick states in the right order, you can do a lot better. It shouldn't really be surprising in some sense that some states are more useful to figure out first than other states. So if you've got some state space and there's a whole bunch of things on the fringe, but there's some sort of bottleneck that you really need to figure out, if you can figure out that bottleneck first, you'll solve the problem faster. And the nice thing about asynchronous dynamic programming is, in fact, I'm not going to prove this, but it turns out that as long as you just select the states, you can select them in any order you want, as long as you continue to select all states eventually. So you have to continue to select every state in your state space infinitely many times. And as long as you do that, it doesn't matter what order you do it in, these algorithms still work. You can order them however you want. So how should we order them? Well, there's three sorts of good ideas that we could use for ordering them. I'll just go through them. One of them is called in-place dynamic programming. The second, perhaps most popular idea, is prioritized sweeping. And the third idea is real-time dynamic programming. So in place, that basically means just changing. It's almost like a one-bit change to your program, or one-line change. So this is what dynamic programming typically looks like. Let's say we're doing value iteration, synchronous value iteration. How would you actually write this thing if you're writing a piece of code? Well, you wouldn't sort of store all of your iterations separately. You typically say, okay, well, there's some old value function, and I want to make a new value function from that old value function. And you basically update your new value function from your old value function. You just plug this into the Bellman equation, and you get a new value function everywhere. And now, once you've done that, you just swap around what's your old and your new value function, and you would run this thing again. And so that would give you this whole succession of different iterations. So the idea of in-place dynamic programming is just to change that. So this is how we sort of loop through all states, and we make sure that we're doing it really sort of effectively in parallel, even though we're actually. So this is how to do synchronous dynamic programming. And the in-place version, all we do is we change that and we say, okay, well, what happens if instead of having a new one and an old one, we just store one copy of the value function? And then we still sweep through all our states, but every time we change our value function, we say, okay, well, that change is probably a good change. We've made progress in some direction. So why wait to use it? So the moment you've updated this value function, it's then used immediately for the next state. And so we still sweep through all states in turn. Every state still gets a turn to be the root in each iteration. But we use whatever progress we've made so far to improve the value function. This can actually work. It can actually make a big difference. So if you imagine there's some problem, I don't know, like imagine you've got a linear problem where you're just trying to figure out how to get again from the start to the goal here. And if you order your states correctly, so let's say we're going to order them in this way, then just in one iteration, in one sweep now through all the states, if you order them starting with this state, then this state, then this state, then this state, then this state, and so forth, you will solve this problem in one iteration instead of 8 iterations, 9 iterations. Okay, so ordering can matter. It's a big question of what the order should be. So the next idea is, well, how should we order states? How do we figure out automatically which states we should update more? And the idea of prioritized sweeping is to use the sort of magnitude of the errors that we're seeing to guide the choice of which state to choose next. In other words, if you look ahead, you can sort of say, okay, well, for some states, the Bellman error is really high. For some other states we've already figured out exactly the right thing to do. It's sort of stabilized. So if we thought on the last iteration that the value function was 10, but on our next iteration we still think the value function is 10, then probably it's not such an interesting state to look at the moment. Whereas if there's another state which is still changing dramatically from step to step, from iteration to iteration, those are probably the ones that we want to focus on the most. So that basically means the ones where the Bellman error is big. So if the Bellman error is big for a given state, then use those states first. Okay. And now we give up on this idea of doing all states in each sweep. We just, at every step, we pick the state with the highest Bellman error and we iterate. So we just keep picking the one with the highest Bellman error, do that one. Now another state's going to have higher Bellman error, we do that one, and so forth. And so after each step, you need to update this Bellman error so you know what's the magnitude that's actually going to be guiding your backups. So we're just picking the states that we believe are the most important to do next in some order, and we're going to push down the error on those states by doing a backup there, which means now you're going to end up picking some different state. Okay. One technicality, you need to know how to go backwards to do this. You need to sort of know what the predecessor states are in order to run this algorithm. Anyway. And this is typically implemented using priority queue. Okay. The third idea for how to turn dynamic programming into an asynchronous idea requires less computation than this previous idea, and it's sort of it's an idea to focus on the things. Now we're imagining that there's, say, some robot moving through some real world, and there's actually sort of a large problem, but the agent is sort of is charting some course through this state space. And the idea is very intuitive. The idea is to say, okay, well, the agent cares more about the states that are close to it. It cares more about the states it's in and the states that are nearby to it than it does about states where it was an hour ago or states that it hasn't got to yet. So how do we focus on those states? Well, the simplest idea is to use the agent's actual trajectories to guide the state selection. So if the agent's walking through some states, well, look at those states, make sure those states are the ones we're figuring out the most. And so now we've got some real-time steps, ST, AT, RT plus 1, these are the states, the actions, the rewards that this agent's seeing. And at every sort of time step t, we're going to pick that state to be the root of that one's going to be the one that we back up, and that's going to become the root of our backup diagram. We're going to focus on that state, ST, and we're going to do one backup. We're going to consider all the things that we could have done from there and update the value function, and then look at the next state the agent actually walked to next. So it's like if I happen to walk up this staircase, at each step I reach, I'll consider all the things I could have done from that step. So like I could have gone left, I could have gone right, I could have gone up, I could have gone down. I'll do one update of my Bellman equation and then move on to the next step. So it really reduces the amount of computation and focuses on just the parts of the state space the agent's actually moving through. That's called real-time dynamic programming. Okay. So that's sort of the end of this synchronous versus asynchronous. Okay, I just want to dwell, this is actually quite an important idea that will sort of recur again through the course. So there's this idea of full width versus sample backups. So what we've done, if you look at these, dynamic programming is essentially something which does like full width look ahead. So for each state that we consider at the root of this diagram, we're doing a full width search. We're considering all actions that we could take and all states that the environment could push us into. It's full width. That's what full width backup means. We're only looking one step ahead, one time step ahead, but we're considering all eventualities that could occur in that time step. And to do this, we need knowledge of the MDP. We need to know, well, what is the transition function and what's the reward function. And this is great, except that it doesn't scale up very well. So dynamic programming could be very effective sort of medium-sized problems. So tens of thousands, hundreds of thousands of states, maybe even millions of states. But it doesn't scale up to really large state spaces or really large action spaces. And what we say it suffers from is something called Bellman's curse of dimensionality. So the curse of dimensionality basically means that if you have some number of state variables describing the state space, then the number of states in that state space grows exponentially. So if you have 20 state variables, then even if those state variables are binary, you've already got 1 million states in the state space. And so if you've got 1 million states, and we're doing something which is 1 million squared times the number of actions per, so each individual backup now has to look at all 1 million possible successor states. and we're going to do 1 million backups to do one iteration of dynamic programming. So even one backup can be too expensive in large problems. So what do we do? So we're going to look at a couple of ideas. The main idea that we're going to use in the rest of this course is to use sample backups instead of full backups. So that means that basically now, instead of considering this full width look ahead, we're just going to sample one transition from that look ahead. We're going to use the dynamics of the problem and sample just one action that we might have taken and one thing that the environment might have pushed us into, and use that as a representative of the whole look ahead. And now basically use a Monte Carlo approximation to estimate the actual value. And what's nice about that is that, first of all, it's model free. So if we're sampling the dynamics, we can actually do that by just sort of running our robot and seeing what it does. So you run it for one step and you see if it took this action, which state did it end up in? You don't need to know the dynamics of the problem, you just observe what actually happened to that agent as it walks through its world. We've got some agent in one of these mazes, and you don't need to know the maze in advance, you just say go north and see where you are. Okay. And it also, and very importantly, it breaks recursive dimensionality through sampling. So what's the cost of one of these backups? Well, it's constant. It doesn't matter what the size of the state space is. We're just going to pick one sample and use that sample. We've broken recursive dimensionality by sampling. Okay. So subsequent lectures, we're really going to focus on how to do this. That's sort of the next couple of lectures, actually, is these looking at how to do the sample-based versions leading to temporal difference learning algorithms. Okay. One more sort of big idea that's useful for large problems. Again, we're going to defer talking about this more to the second half of the course, will be lecture 6, where we start to get into this more. But just in terms of dynamic programming, just to give you a flavor of this idea, another big idea, so sampling is one way to deal with large problems. But we still have this issue that the state space may be enormous. I mean, what happens if, one of the problems I've worked with a lot is the game of Go, it's got 10 to the 170 states to describe the board configuration. So what do? You can't describe the value function for 10 to the 170 states. A lot of real-world problems are like that, and maybe the state space is continuous. How do you describe the value function of a continuous space that a robot's in? You have to approximate it. And the natural way to do that, as you've seen no doubt in the rest of your machine learning classes, is to use a function approximator. So we're now going to represent the value function by a function approximator, where we've got some parameters theta representing the value function now. So we're going to basically estimate the value function everywhere, the value function of all states S, by basically a function approximator, where you pass in that state into your function approximator, and it's got some parameters that uses those parameters to estimate it. So we'll look at this in more detail later. And then the idea is, in this class, the question is, well, how can you apply dynamic programming if you have a function approximator? And the commonest idea is what's called fitted dynamic programming, or fitted value iteration is the value iteration version. So this basically means value iteration using function approximation. And so the idea is basically at each iteration of the algorithm, what are we going to do? Well, we don't want to consider the whole state space, it's too big. So we're just going to sample some states from that state space. And for each of those states in our samples, we're going to look at what would have happened under our Bellman equation. We're basically going to say, look one step ahead using the Bellman equation. And that gives us some target values. So this is kind of, if we were to apply our Bellman equation one step using our current estimate of the value function. So we start in state S, we consider the S primes we might end up in. We do our one-step look ahead, and we say, okay, well that's the target which we'd like our value function to be. The problem is that these targets might not now, that this is some sort of targets that might not be representable by a function approximator, so we have to fit to these targets as well as we can, and we do that by supervised learning. So it's like at each iteration, we're sort of, we've got some function approximator representing V, so if this is our state space, S, and this is our value function, V of S, we're trying to learn the value function over this whole space by sampling some states in our state space. What we're going to look at is from each of those sample states, we're going to do a look ahead, by applying one of these trees and looking ahead from that state. We're going to evaluate the successors by our current v, this is v theta. And now that's going to give us some targets. So it's going to say, okay, well for this point, we wish that our value had actually been here. For this point, we wish our value function had actually been here. And for this point, we think our value function should actually be up here. And then basically iterate and say, okay, well now we're going to use these as the targets for a supervised learning algorithm, fit a new function to these guys, and that's our new value function, and iterate the algorithm repeatedly. So it's a nice idea, it's quite widely used, it doesn't actually converge necessarily, so it's slightly problematic. And we'll see actually, there are some issues once you start to introduce functional approximation into RL, and there's questions over, it's good to know which algorithms actually converge and which don't. This one can work well in practice, but doesn't necessarily converge. And the other big issue is you still need some way to be able to look ahead. So this is only effective or some way to pick useful states or have some sparsity to that part of the function, the transitions. Okay. Any questions before I do just a little bit of theory? Just got enough time to give you an outline, flavor of the theory. Okay. So I don't think I'm going to do this in detail. I just kind of want to give you some sense of why it should be the case. I mean, there's these amazing facts about the Bellman equations that essentially, no matter what you do with your value iteration or with your iterative policy evaluation, you just keep applying this and it gives you a unique optimal value function with value iteration. And that should feel surprising. You should be asking yourself, well, why? How do we know that's true? And so how do we know that value iteration really converges to V star? Or that iterative policy evaluation converges to V pi? And if we don't know that, so we already know that if you do policy improvement, you can make progress, but we need to know that our policy evaluation is doing the right thing. And even if we know that it converges to V star, how do we know that that V star is actually unique? So far we've assumed that. I told you that V star is just, there's this unique V star for any MVP. How fast the algorithms converge, how quickly do they get there? And every single one of these questions is resolved by the same piece of theory, which is called the contraction mapping theorem, or the NAP fixed point theorem. And the basic idea is that we're going to consider this vector space over value functions. So we're going to say, if you imagine that we've got some value function v of s, this basically tells you, if you imagine every single space in this thing, so we've got some value function, and let's say there are just 3 states in our state space. So now we've got basically v of s1. In fact, let's do it with 2 states, because that's going to be easier to draw. So we've got v of s1 and v of s2. It's just a 2-state problem. So now we can say the value function can be represented in 2 dimensions as just a point. So a value function is just a point in this n-dimensional space where there are n states in the problem. And you can imagine that as we run our algorithms like value iteration, what we're doing is we're making a series of points in the space. It's going to be moving around. And what we want to show is that this converges on something, and that the point it converges to is V star. Okay? So this is like V1, V2. We want to show that this progress is actually takes us to something unique, and that unique thing is the optimal value function. And so the way we're going to do that is basically looking at what the Bellman equation does to points in this space. And the basic idea is to show that the Bellman equation brings value functions closer together. In other words, if you apply the Bellman equation to 1v1, if you apply the Bellman equation to some value function over there, and you were to apply the Bellman equation to a different v1 over here, so let's call this v1 prime, that where it would take you to will be closer than where you started. That's called a contraction. If you've got some operator, you apply it to 2 different things. So we could have started with this value function. We could have started with this value function. What we're going to show is that if you apply the Bellman equation to both of these things, you end up at a point that's closer together. And once we've got that property, everything else just falls out. So basically, it means that if you're getting closer and closer together, that these things have to, eventually, if they're getting closer at every single step, doesn't matter where they go, eventually they have to end up getting to the same point. So they have to sort of reach the same point. And intuitively, that makes sense, because what if they didn't? What if there were two separate places that this would converge to? Let's say this was going to converge to something over here, and this was going to converge to something over here. Well, by our contraction idea, we could then just apply the Bellman equation one more time to each of these, and we know that that must get us to something closer than where we started from. And so these can't have converged yet. So the only way these could have converged is if there's a unique point that it converged to. So all we need to show is that there's a contraction. That's the basic idea. All we need to show is that the Bellman equation brings two value functions closer together. And basically we can do that by just looking at the maximum difference between the state values. So we basically want to know if our V1 was 3, this was 3 and 4, and then our V2 was 2 and 1, we would just say, well, what's the biggest difference between these? And the biggest difference is here, where we've got a difference of 3. Okay? So now all we're looking at is the maximum difference at any state. So in this case, it's 3. That's the biggest difference. And we're just going to show that that biggest difference gets closer and closer, is the thing that's this distance function we're using. We're measuring the distance between value functions by this number here. We're showing that gets smaller and smaller and smaller until eventually, when this thing converges, this has to be 0. They have to be the same. Okay. So all we do now is we basically take the Bellman equation, we turn that into an operator. So we're going to say, okay, we're going to start with our B. This is the vector notation. We're going to apply the Bellman equation to it, and you can look at the math afterwards, but it's in the September book as well. I don't really have time to do it justice. But essentially, we can show that this is a contraction. And in particular, it's not just any contraction, it's what's called a gamma contraction, which means it's making value functions closer by some positive amount. I mean, it's making some actual progress at every step. So we start with some value function before, and this is that distance we're looking at. This is the number 3. And we're basically showing here that if you apply the Bellman equation to this thing, you end up getting gamma amounts closer. And because we get gamma amounts closer, what's nice is that we actually know something about the rate at which this algorithm converges. So gamma is the discount factor, and we know that we make at least gamma progress every single step. And that tells us that we get a linear convergence rate. So this is the contraction mapping theorem. This is basically just what I was saying with this diagram, that if you have one of these gamma contractions, then you get convergence absolutely guaranteed to a unique fixed point, and that you get a convergence rate of gamma by just applying these iterations again and again and again. Okay, so that's the theory. Let's just quickly put it back together again. What does that really mean? Well, it means that the Bellman expectation operator, so this is the thing which basically takes our value function and does basically just like iterative policy evaluation. You just apply the Bellman equation, you turn it into an update, and we say that this update process will converge on something unique. And that unique thing is V pi. Okay. And so this means that iterative policy evaluation converges, and that also means that policy iteration converges, because we know that we had the result about policy improvement earlier. Okay. And now we can do the same thing with the optimality equations. We're just going to define an operator again, turn the backup idea into an operator. This is the thing that does the one-step look ahead. If we were to use that as an operator, we can again show that it's a gamma contraction, and therefore, if you were to do value iteration, so one step of value iteration, you just repeat this, you end up at a unique fixed point by the contraction. Okay. Sorry to sort of go through that a little bit quickly. Just got enough time to take questions. So the theory here at the end is non-examinable, but it's there to really, I think it's just worth taking a look at to understand, why, just to know that these things are sound that we're working with. You don't need to understand it well enough to reproduce. What I'd really like you to understand are particularly sections 1 to 4 of this class, where we really get the basic ideas. And I guess the core slides is this. You know, I really want to make sure that you understand these core ideas that we can solve prediction problems, we can solve control problems. There are two ways to solve control problems: by using one of the corresponding Bellman equations, the expectation equation, and doing this policy iteration idea in leading evaluation of improvement, or using the Bellman optimality leading to value estimation. Any last questions?
Only one.
Yeah.
So if we define a huge gamma factor, do we go back to the same point as if we define a small gamma factor?
No, it's different.
It's different.
That's
Just quickly.
It's not just the speed, it's actually a different thing which you're finding. And that should be intuitive from the first lecture where I showed you, second lecture where I showed, last lecture I showed these examples where, like the student MVP, you could have different discount factors and the value function is different.
Yes.
Yeah. So you solve this, it's a different problem, but the speed at which you solve that different problem